Welcome to the deep dive. Ever wondered how, a simple curved bit of glass can fix our sight?
Or let us see tiny cells or distant galaxies.
Exactly. Today, we're diving into lenses, those transparent things that bend light and, well, basically shape how we see everything.
Yeah, it's fascinating stuff. And for this, we've got some great educational materials, really detailed stuff on the different types, their properties, how they actually make images.
Right. So our mission here is to pull out the core ideas, how lenses work, the different shapes they come in, the kinds of images they make. We want those aha moments for you without getting totally lost in the weeds.
Mm-hmm. Clarity.
So let's start basic. What is a lens?
Okay, so at its heart, a lens is just a transparent medium, usually glass, sometimes plastic.
Right.
But the key is its shape. It typically has two curved surfaces, and these are designed very precisely to bend light refracted as it passes through.
So like controlling light beams.
Pretty much, yeah. Redirecting them accurately.
Okay. And that leads us to the two main types, I suppose. Convex and concave.
Exactly. Those are the big ones.
Let's take convex first. What makes a lens convex?
A convex lens, you might also hear it called a converging lens. It's thicker right in the middle, and then it gets thinner towards the edges.
Thicker middle, thin edges. Got it.
And its main job, when parallel light rays hit it, like from the sun, it bends them inwards so they all meet or converge at a single point on the other side.
So it concentrates the light.
Concentrates it. Yeah, that's a good way to put it.
Now, the materials mentioned three kinds of convex lenses.
There's the biconvex or double convex. That's where both sides curve outwards, like a classic lens shape you might picture.
Okay, both sides bulge out.
Then there's plano-convex. One side curves out, the other side is just flat, plain.
Simple enough. And the third one sounded a bit weird. Convevo-convex.
Yeah, convevo-convex. It sounds contradictory, doesn't it? One side curves out, convex, but the other side actually curves in, concave.
How does that still converge light then?
Good question. It still acts as a converging lens if the outward curve, the convex part, is sort of stronger or more curved than the inward concave part. The overall effect is still to bend light inwards.
Okay. So the dominant curve wins out.
Basically, yes. The overall shape still makes it thicker in the middle, overall.
Right. Now, there was a really important safety note in our sources about these.
Oh, absolutely crucial, yes. Never, ever look directly at the sun or any really bright light through a convex lens.
Because it concentrates the light, right?
Exactly. It focuses all that energy onto a tiny spot. It can cause serious permanent eye damage almost instantly.
Wow, okay.
And same goes for focusing sunlight onto, say, your skin or dry leaves or paper. It acts like a burning glass. It can easily start a fire, so real caution needed.
Definitely good advice. Okay, let's switch gears to the other type, concave lenses. How do they differ?
Concave lenses or diverging lenses are pretty much the opposite shape. They're thinner in the middle and get thicker out towards the edges.
Okay, thinner middle, thick edges.
And their effect on light is the opposite too. When parallel light rays go through a concave lens, they get bent outwards. They spread apart or diverge.
So they scatter the light instead of focusing it.
Scatter or diverge.
And like convex, these also come in different flavors.
Similar pattern. You have biconcave or double concave. Both surfaces curve inwards.
Okay.
Then plano-concave. One side curves in, the other is flat.
Right.
And finally, the convexo-concave. Again, one side curves out, one curves in. But for it to be a diverging lens overall, the inward concave curve has to be the more dominant one.
Making it thinner in the middle overall.
Exactly.
Okay, so we have the basic shapes down and what they do to light. Generally, to really get how they make images, though, we need some key terms. First up, center of curvature. What's that?
Right. Imagine extending the curve of one of the lens surfaces so it forms a complete sphere, like a ball.
Okay.
The center of curvature is just the center point of that imaginary sphere. And since most lenses have two surfaces, there are usually two centers of curvature C1 and C2.
The centers of the spheres that the lens surfaces are part of. Makes sense. And radius of curvature.
That's just the radius of those imaginary spheres, the distance from the center of curvature C out to the lens surface itself.
Okay.
And our sources mentioned, just to keep things simpler for now, we're often looking at lenses where both radii are the same.
Gotcha. Next term. Principal axes. Sounds important.
It is. It's the main reference line. It's an imaginary straight line that goes right through both centers of curvature, C1 and C2.
Like an axle through the lens.
Kind of, yeah. And the special thing about it is any light ray traveling exactly along this axis goes straight through the lens without bending at all.
Undeviated. Okay. What about the optical center?
The optical center, usually marked O, is a specific point on the principal axis, but it's located right inside the lens material itself.
Inside the glass or plastic.
Yes. And its unique property is that any light ray passing through this exact point, O, comes out the other side, traveling parallel to its original path. It doesn't change direction, though it might shift sideways a bit. Ah, okay. So straight through the principal axis, no bending. Through the optical center, no change in direction.
Correct.
Now the principal focus, or just focus F, this seems different for convex and concave.
It is very different. For a convex lens, remember, it converges parallel light.
Right.
Well, the principal focus F is the actual point where those parallel rays meet after passing through the lens. It's a real spot on the principal axis on the opposite side from the incoming light.
A real meeting point.
And since light can go either way through the lens, there are actually two foci, F1 and F2, one on each side.
Okay. And concave, since it diverges light.
Right, it doesn't bring parallel rays together, it spreads them out. So if you shine parallel light through a concave lens, the rays diverge on the other side.
So where's the focus?
Well, if you trace those diverging rays backwards in straight lines.
Ah, like where they look like they came from.
Exactly. They will appear to originate from a single point on the principal axis. That point, where they seem to diverge from, is the principal focus of the concave lens. It's a virtual focus point. Virtual because the light rays aren't actually there.
Precisely. And again, two foci, F1 and F2, one on each side, representing where parallel light from either direction would appear to diverge from.
That distinction between real and virtual focus is key, I think.
Yeah.
Okay, last term, focal length.
Simple enough. Focal length, little f, is just the distance from the optical center O to the principal focus F, measured along the principal axis.
The distance from the middle of the lens to the focus point.
Yep, and it tells you how powerful the lens is. Shorter focal length means a stronger lens, more bending power.
Okay, great. Those terms really help build the picture. Now, one of the sources had this neat analogy, thinking of lenses as stacks of prisms.
Ah, yeah, that's a really helpful way to visualize the bending. Imagine slicing a convex lens horizontally.
Okay.
Because it's thicker in the middle, each slice acts like a tiny prism with its base pointing towards the center, the principal axis.
Right. Prisms bend light towards their base.
Exactly. So all those little prism slices bend the parallel light inwards towards the axis, making it converge.
Nice. And for concave.
Opposite idea. Slice a concave lens, which is thinner in the middle. Now each slice is like a prism with its apex, its pointy bit, towards the principal axis.
And prisms bend light away from the apex.
Towards the base, which is now pointing outwards. So they bend the light away from the principal axis, making it diverge.
That really clarifies the mechanism. Bases together converges, apexes together diverges.
Cool. Okay, let's shift to the images formed. Real versus virtual images. What's the difference?
The key difference is whether you can project the image onto something. A real image can be formed on a screen, like a movie projection.
Right.
It's formed where the light rays actually intersect after passing through the lens. And a key thing, real images formed by a single lens are always inverted upside down.
Upside down and projectable. And virtual.
Virtual images cannot be projected onto a screen. Your eye sees them, but they aren't physically located where they appear. They form where the rays only appear to intersect if you trace them back.
Like a reflection in a mirror. Exactly like that. And virtual images from a single lens are always erect or right side up.
Okay, real, projectable, inverted, virtual. Not projectable, erect. Got it. Now, let's get specific with convex lenses. How the image changes depends hugely on where the object is, right?
Absolutely. It's quite dynamic. Let's start with the object super far away, basically at infinity, like a distant star.
Okay. Infinitely far.
The light rays coming from it are essentially parallel. So the convex lens converges them right at the principal focus, F, on the other side.
So the image is at F. What's it like?
It's real, it's inverted, though hard to tell when it's just a dot. And it's highly diminished, just a tiny point of concentrated light.
That's the burning glass principle again.
Precisely, focusing the sun's parallel rays.
Okay, bring the object closer.
Right.
Say beyond 2F, further than twice the focal length away.
Right, now the image forms between F and 2F on the other side. It's still real, still inverted, but now it's just diminished, or smaller than the object, not a tiny point.
Smaller, real, inverted, between F and 2F. Any applications bring to mind?
Cameras. A camera lens takes the larger scene and forms a smaller, real, inverted image on the sensor or film inside. That's exactly this setup.
Of course.
Okay.
Good. Move the object right to 2F. exactly twice the focal length.
This is a neat symmetrical case. The image forms exactly at 2f on the other side. It's real, it's inverted, and crucially, it's the same size as the object.
Same size. Where would you use that?
Some photocopiers, the old school ones anyway, use this principle to make an exact 1.1 copy. Lens forms a same size real image on the drum.
Interesting. Okay, keep moving it closer. Object between f and 2f now?
Right. Now the image forms beyond 2f on the other side. It's still real, still inverted, but now it's magnified larger than the object.
Larger, real, inverted, beyond 2f. Uses.
Projectors. A slide projector, or even a digital projector, takes a small object, the slide or the display chip, placed between f and 2f, and throws a large, real, inverted image onto the screen way beyond 2f.
Right, and microscopes too. The first lens.
Yes, the objective lens in a microscope works like this, creating a magnified real image inside the tube for the eyepiece to then magnify further.
Okay. What if we put the object right at the focal point, f?
At f, well, the rays coming out of the lens become parallel. They don't converge.
So, no image.
Theoretically, the image forms at infinity. It's considered real, inverted, and infinitely, or at least highly, enlarged.
Wow. Where's that useful?
Think about searchlights or spotlights. You put the bright bulb right at the focus of a convex lens or reflector. What comes out? A powerful parallel beam of light that travels a long way.
Sending the light out to infinity,
Yeah.
effectively.
Oh?
Okay, one more step. Move the object inside the focal length between f and the lens itself.
This is the magic zone for magnifying glasses.
Right.
When the object is closer than f, the rays coming out of the lens are diverging. They don't meet on the other side.
So no real image.
No real image, but if you look through the lens from the other side, your eye traces those diverging rays back.
And they seem to come from a point behind the object.
Exactly. On the same side as the object. Your brain creates a virtual image. And this image is erect, right side up, and magnified, larger than the object.
That's the magnifying glass effect we all know. Virtual, erect, enlarged.
That's the one. Only happens when the object is within the focal length.
So convex lenses are really versatile. Real images, virtual images, smaller, same size, larger. Depends entirely on object position.
It really does.
What about concave lenses then? Are they as complex?
Actually, no. Concave lenses are much simpler in terms of image formation.
Oh, how so?
No matter where you put the object in front of a concave lens, far away, close up, it doesn't matter, the image formed is always the same type.
Always. What type is that?
It's always virtual, always erect, right side up, and always diminished, smaller than the object.
Always virtual, erect, and smaller. Where does it form?
It always forms on the same side of the lens as the object, somewhere between the optical center O and the principal focus F.
Huh. So much more predictable.
Very predictable. You can see it with ray diagrams.
Mm-hmm.
A ray parallel to the axis diverges, as if from F, a ray through O goes straight. Where they appear to cross back on the object side, it gives you that small, virtual, upright image.
Okay. Consistent, if maybe less flexible than convex. Now, our sources had a practical tip for finding the focal length of a convex lens.
Ah, yeah, the distant object method is pretty neat.
How does it work?
You take your convex lens and point it towards something really far away, a tree across the street, a distant building. Assume the light rays from it are basically parallel.
All right.
Then you take a screen, a piece of paper works fine, and hold it on the other side of the lens. You move the lens back and forth relative to the screen.
Until you get a sharp image on the paper.
Exactly. A sharp, inverted image of the distant object. Since the incoming rays are parallel, they're focusing at the principal focus, F.
Ah. So the distance between the lens and the screen at that sharp point is the focal length.
Pretty much, yes. It's a good approximation of F. Simple and effective.
Cool. Okay, let's talk applications. We touched on some, but let's round them up. Convex lenses, where do we see them most?
All over the place, really. Optical instruments are major users. Cameras, as we said, projectors, telescopes, microscopes, they often use combinations, but convex lenses are key components.
Right.
Then simple magnification, reading glasses, magnifying glasses,
Right.
and importantly, in eyeglasses for correcting farsightedness, hypermetropia, helping people focus on near objects.
So they help bend the light more effectively for farsighted eyes.
Precisely. Adds converging power.
And concave lenses, what are their main gigs?
Their big one is correcting nearsightedness myopia.
So the opposite problem, trouble seeing distant things clearly.
Exactly. A nearsighted eye focuses light too strongly in front of the retina. The concave lens diverges the light slightly before it enters the eye.
So the eye's natural lens can then focus it correctly on the retina.
You got it. It reduces the overall focusing power just enough. They're also used in some telescope designs, like the Galilean telescope.
Okay, so primarily vision correction for myopia and some specific telescope uses.
Yeah, covers the main ones, yeah.
Great. So just to quickly summarize the core differences again, convex versus concave.
Sure, shape. Convex is thicker middle, concave is thinner middle.
Right.
Light. Convex converges parallel light, concave diverges it.
Converge versus diverge.
Images. Convex can do real, inverted, various sizes, or virtual, erect, magnified, depending on object position. Concave always does virtual, erect, and diminished.
Always virtual, erect, smaller for concave. That's a really clear distinction. And there was one last little nugget in the sources about combining surfaces and materials.
Ah, yes, getting into more advanced optics. First, many eyeglass lenses aren't just simple plano-convex or whatever. They often have complex curves on both surfaces to really fine-tune the correction for a person's specific vision needs.
Tailor-made curves.
Exactly.
Yeah.
And the other point was about chromatic aberration.
Collar fringes.
Yeah. Simple lenses tend to bend different colors of light slightly differently. Blue light bends more than red light, for instance.
Okay.
This can make images look fuzzy or have colored edges, especially in things like telescopes or binoculars.
Not ideal for sharp images.
Not at all. So, lens designers figured out that by combining a convex lens made of one type of glass with a concave lens made of a different type of glass, they could make the color distortions from one lens cancel out the distortions from the other.
Clever. Combining them cancels the color errors.
It's called an achromatic doublet, and it's crucial for high-quality optics. Gives you sharp, true color images.
Amazing how much complexity goes into making these things work so well. Okay, so wrapping up this deep dive, we've looked at convex and concave lenses, what
Right.
they are, how they bend light converging versus diverging.
We define those key terms: center of curvature, principal axis, optical center, focus, focal length. They're the building blocks for understanding.
Definitely. And the big difference between real images, which you can project, and virtual images, which you can't. Plus, how that plays out so differently for convex lenses depending on where the object is.
Compared to concave lenses, which are always virtual, erect, and diminished. Consistent, but different.
Right. We hope this breakdown gave you, our listener, some of those aha moments, making sense of how these essential bits of optics actually work.
Yeah, hopefully bringing some clarity to it all.
Absolutely. And just to leave you with something to think about, these ideas of converging and diverging focusing, they don't just apply to light, do they?
Interesting point.
Think about how you focus your attention. What information do you let converge to form your understanding? What different perspectives might act like diverging lenses, broadening your view? What are the metaphorical lenses shaping how you see the world? Something to mull over.